everyone. Thank you for joining us this morning. I'm Alicia Hyatt, the editor of Canadian Mining Journal, and we are very proud today to bring you today's webinar with John Crane. Experts from John Crane are going to take us through the latest evolution of sealing technology and how this technology can be applied to improve the longevity and reliability of your mining equipment, save water, and save on costs. Today's webinar will consist of a pre-recorded presentation with several experts from John Crane participating. After the roughly 40-minute presentation, we're going to come back live with all 4 experts and answer any questions you have. So now I'm going to turn it over to John Crane's marketing manager, Elsa Cantu, who will be leading the pre-recorded discussion, and then we'll be back live in 40 minutes.
Good morning, everybody, and welcome. This is a John Crane webinar titled Improve Reliability, Bottom Line, and Water Usage with the latest evolutions in sealing technology. My name is Elsa Cantu, and I'm the marketing manager here at John Crane. I'll be facilitating our discussion for today. We have an expert panel here to discuss and share some of their strategies that John Crane has developed over the years. But first, I'm just going to go over a couple of household items. Just so you know, this is a previously recorded session, but we still will have everyone on mute. We'll have everyone on mute throughout the session, and then we'll open it up at the end for discussion. We are sensitive to the time that everybody's afforded us, so we want to make sure that we end the session at the top of the hour or come as close to that as we possibly can. Remember to put your questions in the Q&A chat, and any questions we are unable to respond will be answered and shared with attendees with a follow-up email. So again, welcome. Thank you for joining us, and we're going to go ahead and jump right into it and introduce our panelists for today. I'd like to begin today with introductions. I would like to start with Warren Smith. Warren Smith is our global mining community leader and coordinator. He's worked with John Crane for over 33 years and has extensive experience in rotating equipment, processing, applications across the mining and minerals market. So Warren, what are some of the trends you are seeing when it comes to sealing pumps and critical rotating equipment in mines, such as increasing uptime, reducing water waste, etc.?
In mining operations around the world, there are multiple options for sealing slurry pumps. We find that the geographical location, economic, and environmental issues play a key role in which option is chosen. Without any doubt, packing remains the go-to solution for sealing slurry pumps that both the pump OEMs and the mine operators embrace. With that said, today's mine operators are able to choose from third-generation packing technologies through engineered heavy-duty single and double slurry seals. Packing and mechanical seals on offer today are constantly evolving to meet the economic and environmental issues mine operators are faced with.
So Warren, are there choices that operators can consider when leaning towards packing?
Definitely. Packing yarn technology is constantly changing. We have moved away from first-generation base yarns like cotton, jute, flax, and asbestos, which typically include PDFE and graphite as the sacrificial lubricant or the blocking agent. Asbestos and graphite packings consume high levels of energy and require a leak rate of up to 60 drops per second per OD inch of shaft for cooling and lubricating. This means a typical 130 millimeter or 5-inch shaft would need to leak at a rate of 300 drops per second. With second-generation yarns, we saw the introduction of both aramid, which is Kevlar, and ePDFE GFO packings entering the market, and they are still playing an important part in our packing portfolio today. Today, our go-to products would be carbon yarns and graphite yarn packings, possibly even supported by the hybrid technologies. we are able to combine packing styles to offer solutions that reduce shaft wear, energy consumption, and solutions that leak as low as 8 to 10 drops per OD inch of shaft.
So Warren, when when do you decide to make seals a consideration?
Well, the driving force behind upgrading from packing to mechanical seals is driven by the need to increase reliability of rotating equipment, meet the needs of in-country environmental regulations, such as energy reduction and water consumption. A typical mine would see anything from 60 to 120 liters of water being used per minute per pump as Gland service water to gain optimal life out of entry-level packings. In turn, these pumps are prone to high shaft wear and excessive leakage, which results in premature bearing failure, ultimately leading to a higher maintenance cost and reduction in mean time between failure. This has seen the introduction of engineered slurry seals, for example, the John Crane Type 5840 single slurry seal, which can be installed in applications containing solid contents of 60% by weight at 21 bar. With our heavy-duty 5860 seal offering, we are able to operate in a window of 35 to 40 bar in applications containing, well, that's applications containing solids by weight, once again with little to no flush.
Warren, what are some of the strategies to increase the reliability of your pumps and rotating equipment so that you can positively impact your organization's bottom line, such as upgrading your packing, component seals, or mechanical seals?
The mining industry today is fortunate to have multitude of options for upgrading applications that are deemed critical or require regular maintenance. The first available option is simply to upgrade the style and configuration of packing used. By combining newer yarn technologies, John Crane offers an engineered packing solution to extend the life of packing sets. This includes combination yarns and others. Let's take a look at two examples of packing upgrades in sub-Saharan Africa. The first is a combination packing set, which was used to increase the mean time between failure on a number of tailing pumps at a mine waste dump processing plant. The packing sets used were made up of a single ring of John Crane style K1730, which is our Kevlar packing, with a balance of the set being either 3 or 4 rings of style C1065, a GFO-based packing. This has seen the mine operator go from a mean time between failures of 7 to 14 days to between 30 and 45 days. This is an impressive improvement of around 350%. Since the initial John Crane packing set installation, the annual packing costs have been reduced from £720,000 to £50,000 per annum, a massive saving. The second example involves an engineered packing solution to remedy the mine operator's request. John Crane and 4 other manufacturers were asked to develop and test packings to extend the mean time between repairs of 25 slurry pumps on a titanium mining facility on the east coast of South Africa. For this, John Crane's engineering team chose to modify our style K1771, a meter aramid packing, by reinforcing the corners with a spun Kevlar yarn and implementing a rubber core to increase its resilience. With the implementation of our recommendation, the mean time between repair has improved from 1 month to 7 months. In turn, the added graphite coating has eliminated problems related to premature sleeve wear and failure. With that said, we should not forget that the single biggest gains will come from transitioning from the use of mechanical packing or gland packing to an engineered slurry seal.
Those are some great examples, Warren. I guess if we transition over here to Steve, Warren offered some examples for us. From your perspective, what are some of the strategies to increase reliability of your pumps and rotating equipment so you can positively impact the mine's bottom line?
So you like what you heard from Warren on how to optimize your pack pumps, and you're thinking now that you'd like to take one more step and start enjoying the benefits of mechanical seals. Okay. The single biggest sealing technology option available to the mining industry to improve pump reliability and bottom line is to upgrade to mechanical seals on the pumps that are critical to your operations and the ones that require the highest levels of maintenance. I'd say filter feed and tailings pumps are good typical examples. We've seen by simply transitioning from gland packing to mechanical seals, mining operations have been able to do away with daily and weekly maintenance schedules on tailings lines and run uninterrupted for 12 to 18 months. And they've even enjoyed multi-year runs on the filter feeds. This results in significant maintenance cost savings, reduced equipment downtime, and let's not forget about the potential water savings that Warren just mentioned. In some cases, we're seeing 120 liters per minute per pump savings in water. Significant.
Could you give us a quick description of the basics of mechanical seal technology and what differentiates seal design found in mines or the mining industry from those used maybe such as a refinery or a municipal water pump?
Sure. Let's see, mechanical seals, the basics. So all mechanical seal technology relies on a very thin film of lubricant between a rotating and stationary set of very flat wear faces. Now, whether this lubrication is provided by the fluid being pumped or by an introduced fluid, the consumption of this media is extremely low. And it is this set of faces that prevents what's inside a pump from escaping to the atmosphere. And along with these faces, there are support components such as springs, O-rings, and drive mechanisms that all work together to allow the seal to do its sealing job. Correct design choices and proper engineering can minimize or eliminate the need for external fresh water. So now we're going to look specifically at slurry seals. So mining slurry is a technically challenging application for mechanical seals. That's probably a rather large understatement. Key factors we need to address before settling on a final seal system design are the solids percentage in your slurry, particle hardness, particle size. All important drivers needed to come up with a correct seal design. John Crane employs a lot of design features in our slurry seals that are specifically meant to give our seals the reliability and ruggedness required by unique mining conditions. Seal face designs are optimized to handle a lot of abuse in rough operating conditions. We use premium grade silicon carbide face material as a standard, or an advanced silicon carbide that uses controlled density material that is very good at scavenging water out of the slurry to keep the faces lubricated in poor conditions. Heavy-duty drive mechanisms give the positive torque transmission that these demanding applications require. And we also use low modulus springs to give up to 8 millimeters or almost 3/8 of an inch axial tolerance. Big numbers. And they're positioned within the seal so that they are protected from the product. Or we also use non-clogging cone spring designs, and the profile of the cone spring assembly has been designed to remain effective and even resist scale buildup or product ingress that would render normal springs or bellows inoperable.
Yes, Steve, in considering the transition from packing to mechanical seals, what should the user expect? How would that change be executed?
Well, if you do it right, one thing you should expect right away is less housekeeping. I've seen high pressure tailings trains go from a constant spraying, spewing mess to a dry, shiny showpiece. The morale boost to the maintenance department alone, worth the effort. So what's involved in getting from a pack pump to a nice, dry, well-behaved, reliable, water-saving mechanical seal? There are a variety of pump applications at a mining operation, but today let's talk about the fun ones, our big, heavy-duty slurry pumps. What is needed here? Slurry seals are almost always bigger and beefier and need more room than their puny little antsy friends. The good news is that most of the big slurry pump brand designs lend themselves quite nicely to using different sealing methods. And there are a variety of adapters and hardware available from the pump OEMs that allow the use of pack stuffing boxes, expeller seals, or good old mechanical seals. All of the major slurry pump companies will have complementary relationships with the major mechanical seal companies. I've had help with locating flush holes from a large pump outfit in Wisconsin. I've gotten liner info from another in Seneca Falls, New York. I've had help with housings from a big one in Arizona and stuffing box info from a well-known company in Finland. Typically, but not always, the entire stuffing box is removed and the seal is designed to bolt up in the same location with the help of a pump OEM adapter or one integral to the seal and supplied by the seal vendor. This is usually quite turnkey, but if you run into something odd, your seal technical rep will take field measurements and most likely get their engineers in touch with the pump company engineers and come up with a plan.
So when switching to mechanical seals, are there any special considerations that we need to address with regard to the pump hardware?
Well, the true pump hardware experts are, of course, the pump OEMs, and this is where a healthy working relationship with these companies proves its worth. I have made a few general observations with regard to how slurry pump design may affect mechanical seal performance. One in particular is sleeve material. It's standard practice to replace the old worn packing sleeve when you're converting to a mechanical seal. Just make sure that your seal supplier cares about your sleeve material. Trying to attach your nice new seal to a high chrome, super hard pump sleeve with soft stainless set screws is a recipe for disappointment. Another understatement. The most rugged, high-tech seal is no good to you if it's not going to hang on for the ride. High-pressure applications in particular equal high thrust. For your mechanical seals, you need to get a grip. Slurry pump liners, the wear liners. A lot of slurry pumps allow for an open or closed liner in the area between the mechanical seal and impeller. Which one is preferential with regard to seal reliability varies depending on the specific seal and application. Physical space requirements, erosion effects, heat removal, water use, these are all factors that need to be discussed between the mine and the pump OEM and the seal manufacturer. Impellers, back pump out vanes or no back pump out vanes. Usually your seal would rather that you use an impeller without back pump out vanes, but the importance of this choice, again, depends on specific applications. Have the talk. That three-way healthy relationship with the mine experts, the pump OEM, and the seal people, very important.
So what should we be aiming for as far as equipment conditions go? And how about dealing with impeller adjustments?
Well, it's recognized that a typical seal spec can be pretty fussy, we admit. And when this comes up around equipment conditions and run-out checks, we also recognize that slurry pumps are rugged beasts that expect their neighbors to be as tough as they are. So there is, fortunately, a happy medium. Slurry seals are tougher and more forgiving than their thoroughbred refinery seal cousins. But we would like to see dial indicators used and a fresh set of bearings for initial installs, in particular. Barrel alignment and pump frames being square with the shaft, very important. And we need to talk about impeller adjustment routines too. Are the pumps being routinely adjusted or not touched again until the next overhaul? Well-designed slurry seals can handle a lot of impeller adjustment, but it's important to know about before settling on a final seal design.
Steve, do mining slurry seals require external water, and are there considerations that should be taken regarding what source the mine should be supplying, if any?
Very good question. Well, goal one is to reduce water use, preferably to zero, but many times we do need at least a little to maximize seal reliability. So part of the seal application procedure is finding out upfront, definitely not on the day of install, what water, if any, is available and how reliable it is. Are we going to be using processed water? Are we use reclaimed water, raw water, filtered water, potable water? Are there dedicated flush water pumps, or will we be using a plant-wide water system that drops 20 psi every time someone uses a hose? Or should we go with a standalone system supplied with the seal? Different designs and materials have different needs, but tell us what you have and we'll find a way to accommodate it. And if we need it all, and we can talk about grease too. Always keep the primary goals in the forefront: improve reliability and decrease water use.
Thanks, Steve. Could you comment on any recent developments in seal face technology that would allow mines to further reduce water usage and improve equipment reliability?
I think I'm going to swing it over to Mike now. Mike Caladimas to have a chat.
Thanks very much. Yeah, the approach that we've been talking about here is how to manage the major challenges in a mine, and certainly when we get down to seals, even packing, it's clear that the major challenge is lubrication, and in the case of an end face seal, it's seal face lubrication. So this is a view of a seal face that was not properly lubricated. As Steve mentioned, water conservation efforts have led to more demanding applications for seals, and this is an example of how that seal can fail as a result of poor seal face lubrication. An answer to that question about seal face lubrication can be higher pressure water. Higher pressure water flushes that would force water between the seal faces, but there's actually a better, more elegant method referred to as upstream pumping dynamic lift seal face technology. If we look at how that spiral groove can behave in an upstream pumping dynamic lift situation, the next slide will show us how that works. On the left, there we can see the spiral groove, which is a micro-machined depression, a series of depressions in the seal face. And on the right, we see what that seal face does. In this case, it takes the barrier fluid in. It intakes the barrier fluid at the wide portion of the groove, and through diminishing area, increases pressure at the point of the groove. Well, that's interesting and fascinating and stuff, but basically it presents a nonlinear pressure profile across the seal face. With that comes a very high pressure water lubricant. If water's the barrier, a barrier lubricant is increased in pressure, and we can see that at that red point on the right side of the FEA analysis that shows that diminishing area creating a high pressure of barrier fluid at that point. The next slide sort of shows how that pressure profile looks across the face. It's not just high pressure on the seal face. It's from a flush fluid. This is a self-contained lubrication format where the spiral groove creates its own high pressure, and it pumps a small, tiny amount of barrier fluid, in the case of a mine, typically water, across that seal face and imparts a very small flow. That flow precludes the contamination of the seal face from slurries, or in the case of, you know, common mining applications, from tailings. The next slide is actually an animation slide, and this is sort of a water droplet view. This will be a water droplet view of the barrier fluid passing through a dynamic lift upstream pumping seal. So the important thing to keep in mind here, the takeaway, is the water inside the seal is at low pressure, probably about 20 psi. We can see that lower barrier pressure is much lower than the process pressure. In many cases, it's a fraction of the process pressure. But the spiral grooves, you'll see here, take in that water, force that pressure to increase, and create a tiny flow of clean water across the inboard face. So what this does is really address, there's our nonlinear pressure profile. What this does is really address this key feature of mine sealing reliability, and that is lubrication and seal face, you know, cleanliness and hygiene. So the fluid film thickness in the case of water is much more viscous than a non-contacting fluid like air or nitrogen, where other non-contacting seals have been applied. This is the same basic technology, however, used with a much more viscous barrier fluid. So if we switch to the next slide, we can see how that is arranged. And the preferred arrangement of this spiral groove technology in a slurry seal presents the spiral grooves on the inboard side of the seal, and on the outboard side of the seal, we can see a conventional contacting seal running in water, low pressure water, probably 20 psi water. So its sealing challenges are very, very minimal, and it has a pumping ring on the OD of it, so it forces some of that barrier water down under the inboard of the inboard seal, under the ID, the inside diameter of the inboard seal. So that red face on the inboard side is running against a green face, and the green face is representing the mating ring, and that's the part with the spiral grooves on it. As that shaft rotates, those spiral grooves create that pressure and force a tiny amount of water, probably 1/100th of the water use of a conventional seal, inboard among the pumpage. So what this addresses directly is seal face wear. Since it's non-contacting, seal face wear is virtually eliminated, even in very high pressure, up to 35 bar tailings applications. So very challenging applications have been very successfully sealed with dynamic lift upstream pumping lubrication at the inboard. If we look at the next slide, we'll see some used faces from a tailings application. Obviously, they look brand new. They are operating, keep in mind, in 20 psi clean water. And at the point of the groove, the pressure is much, much higher. But basically, the whole seal is operating in a low pressure barrier, and it creates its own seal face lubrication. So we deliver that water through a very simple system. The next slide shows a very simple water delivery system. This is one that is completely unpressurized. So we're just operating on the head pressure of that stainless steel box full of water, which feeds the seal. And the seal uses that low pressure water. The grooves pump it to a much higher pressure into the process. So as the grooves rotate, they create their own pressure. This is a very simple system. This system can also be delivered as a pressurized system. So where we encounter much higher pressures, we can pressurize that water up to whatever is required, up to probably about 100 psi, if we're pumping against a very, very high pressure. but the system addresses the most I think the most common problem in mining applications, and that's seal face lubrication and wear.
All right, well, thanks, Mike. I think now we can shift over to Tyler. Tyler, we heard about dynamic lift seal face technology to increase pump reliability and mining applications. Are there any other face technologies which would help solve other challenging problems in the mining industry?
Well, good question. There are. The one I'm excited to be discussing today is John Crane Diamond. So what is John Crane Diamond's seal face treatment? This seal face treatment solution we do in-house at John Crane to bring the features and benefits of natural diamond, one of nature's hardest materials, to improve mechanical seal reliability and pump productivity, especially in mining applications. As Warren, Steve, and Mike mentioned, the big theme here is improving mechanical seal reliability while reducing operating costs. In many cases with John Crane Diamond, we are able to achieve both of these objectives. Our products are based on ultra nanocrystalline diamond, or UNCD technology, which is a proprietary and patented pure diamond material grown on the working face of the mechanical seal ring through a chemical vapor deposition process. The product itself is actually a thin film of diamond on the mechanical seal ring's working face. The thickness of the diamond film is about a quarter of the thickness of human hair. And this is really all the thickness that we need to capture the tremendous features and benefits of diamond for mechanical seals. Our product is a drop-in solution to increase performance and solve challenging problems for existing seals as well as newly installed seals. And then finally here, our diamond face treatment is optimized to run against any hard face material, most commonly silicon carbide, tungsten carbide, and diamond itself.
Now, you mentioned that the features and benefits of diamond can improve mechanical seal reliability and pump productivity. Can you tell us a little bit more about these features and benefits of diamond when it's applied to a mechanical seal face? And can you also tell us more about specific challenging applications where those features and benefits might shine?
Before discussing the features and benefits, I would like to show some properties of diamond. So shown on this slide is a number of diamond properties, and the properties that make diamond an excellent material for rotating equipment are the ones that are specifically bolded in black here. So we've got hardness, high thermal conductivity, low friction, and chemical inertness. And so these properties of diamond really play a role in the features and benefits of diamond as a material for mechanical seals. So shown on this slide is a list, and I'll walk through each of these in a little bit more detail. So the first and probably most obvious is that diamond is one of nature's hardest materials, and the benefit of this on a mechanical seal face is that it exhibits significantly reduced face wear and an impressive resistance to abrasion when compared to traditional seal face materials. This results in the value to our customers being increased mean time between repairs due to the reduced wear, especially. Challenging applications where the hardness of diamond shines is applications where abrasion resistance is critical. So these applications include some of the most demanding abrasive applications in mining and mineral processes where the media contains solids or abrasive particulates. Our diamond face treatment is routinely being used in these applications and has even demonstrated that single seals with diamond faces in certain applications can effectively replace dual seals with processing media containing up to 70% solids. It also should be noted that diamond seals have given customers a cost-effective mechanical seal solution in applications where previously really only packing was used. So why diamond? Just to drive the point home again, due to its extreme high hardness. Note here that As I mentioned, our diamond is optimized to run against any counter hard face. However, when using diamond as a solution to challenging slurry applications, we do recommend using diamond versus diamond on both seal faces so that you get the benefits of diamond's abrasion resistance. To build on this point, shown here on this slide are some textbook examples of face damage from abrasive wear on traditional seal face materials. This wear happens on all varieties of traditional seal faces, and so if you ever see an application where this is happening, this is a great time to consider using John Crane Diamond as a solution.
So Tyler, can you provide some specific application examples of where John Crane Diamond has been utilized in mining applications, and maybe a solution to any sort of challenging or abrasive slurry application?
Yeah, glad to do that. So I'll go over two really quite amazing examples where diamond has performed well in slurry applications. The first is an abrasive mining slurry application. The process fluid of this application is an extremely aggressive mining fluid, pumping 50 to 70% solids. And the other thing to note here is that it's on very large pumps with shaft sizes ranging from 160 to 250 millimeters. The seal we provided here is a single O-ring pusher seal supplied with John Crane Diamond on the seal faces, and this replaced the incumbent gland packing, which required 9 gallons a minute of cooling water. The outcome resulted in end user success, and due to this significant reduction in cooling requirements by switching from packing to mechanical seals with diamond faces has resulted in the customer deploying the similar setup in 50 seals in similar applications. The second story I'll cover is a caustic abrasive slurry application. The operating details of this caustic mud slurry was running at 100 psi, 158 degrees Fahrenheit, and 1440 RPM. The seal details, here we supplied two type 5840 John Crane slurry single seals with diamond faces, and in this application we also replaced the incumbent gland packing technology, which required a good deal of cooling water. The outcome here was that the MTBR exceeded customer expectations by a factor of 3 times, and after our initial trial run, the customer elected to install 8 more pumps with the John Crane Diamond faces.
Can you address some of the features and benefits to diamond and how some people currently on the webinar might be able to capture value from using diamond seal faces?
Yeah, so moving along to the other features and benefits, another key feature for diamond seal faces is their extremely low coefficient of friction. John Crane Diamond Seal's coefficient of friction is only about 18% of carbon versus silicon carbide, and only about 11% of silicon versus silicon's coefficient of friction. The benefit of this results in less heat generation and reduced energy consumption. These benefits enable diamond seals to, 1, address demands of poor lubricating and volatile media, and this leads to an increase in MTBR, and 2, it significantly reduces the seal's cooling requirements, which means reduced auxiliary cooling costs, and it could even mean increased pumping efficiency in seals which use a Plan 11 and other common process fluid flushes. Third, the reduced energy consumption, which comes from the reduced frictional losses, leads to a real reduced electricity consumption and reduced operating costs. In fact, the power consumption savings for diamond seals is significant enough that, depending on the application, we can see payback periods of 12 months or less for the diamond treatment with respect to power savings alone. So challenging applications where the low coefficient of friction of diamond shines are, again, applications where poor lubricating media or temperature sensitive conditions exist. So this includes applications with multi-phase fluids, so fluids where there may be gas entrainment, froth pump applications, so flotation and separation processes, and also end of flow pumps. In these applications, the low friction of diamond and the reduced heat generation means that the fluid may stay a liquid longer, giving the seal faces more lubrication. Also included here are applications where auxiliary cooling is costly and troublesome, and in some cases maybe not available. Diamond provides a potential solution to more complex alternatives where cooling units may be necessary with traditional seal faces. And so again, shown on this slide are some more textbook examples of face damage. The damage shown here is specifically from poor lubrication on the seal face. These failure mechanisms are typically referred to as heat checking, and this commonly results in increased leakage for the seal. Furthermore, sometimes enough heat is generated with traditional seal faces which cause secondary elastomer seals, so O-rings, to overheat and be compromised, which could result in failure for the seal as well. Whenever face damage like this is apparent, this is a great time to consider using John Crane diamond as a solution. The third main feature of John Crane diamond is that it can withstand intermittent dry running situations and other operational upset conditions. This is one of the biggest areas where we see diamond used as a solution, and the benefit of diamond being resistant to operational upsets leads to more predictable lifetime as well as an increase in MTBR for the seal. Challenging applications where this benefit shines is in applications where operational variability and upset conditions occur. So shown here on the slide is a graphic of market research completed, which shows pump failures by component. On the left side of the graphic, you will see that mechanical seals account for more than 2/3 of pump failures. And if you look and take a deeper dive on the right side of the graphic, you'll see that a substantial amount of these seal failures and pump failures stem from operational issues. These are often unscheduled events running the seal outside of the design envelope or from other unintended variations in the operations. The applications here, again, just to drive it home, would include intermittent dry running, commonly seen where pumps start and stop, and could occur in applications like loading pumps, transfer pumps, and batch pumping processes. Other applications would be a very minor cavitation and other unintended operational conditions. So why diamond here? This is due to the design of the surface metrology and the extreme hardness of diamond. The texture and the hardness of diamond reduces seal face damage during these extreme conditions, and depending on the excursion, the diamond treated seal may continue to be fully functional, where a non-diamond treated seal might have catastrophic damage and would require a repair or replacement. And then the last two main features that I'll run through quick here is the next one is that diamond exhibits extreme chemical resistance, which means it's suitable for acids and bases, which may be used in some mineral processing applications. Diamond is highly inert in both acids and alkaline environments and improves the chemical resistance and overall life of mechanical seals beyond the capabilities of silicon carbide. And then finally, our diamond product is optimized to run against any hard counterface, as I mentioned previously, most commonly silicon carbide, tungsten carbide, and diamond. And this benefit of increased material options leads to an optimized ROI for our customers.
Tyler, can you tell us a little bit more about the current availability of John Crane diamond product?
Yeah, so as mentioned previously, our John Crane diamond product can be used as a drop-in solution to increase the performance of many of our widely used seal families. We are maintaining a significant inventory of diamond-treated rings in both the US and Europe for the Type 5600 universal cartridge seal family. These seals are commonly used in the ANSI pumps, which Steve had briefly mentioned earlier. Additionally, diamond-treated seal faces are readily available for most John Crane family of seal products, including the mining-centered products such as our 58 100 slurry seal family, so the type 5840, 5860, and 5870, as well as our type 586 slurry seal. And then finally, the next few seals shown here, like the type 48 family, the type 48 VBF boiler feed water, and other high performance sealing solutions. This may not necessarily belong in a mining webinar. However, this I'm showing here as a testament that the product is intended to run in many of our customers' most rigorous applications.
Hi, everyone. We are back live with our expert panel from John Crane. I'll ask everyone to turn their cameras on. Thanks very much. I'll just introduce everyone on the panel here. Warren Paul Smith is the global mining community leader / coordinator with over 33 years of experience in rotating equipment and processing applications across the mining and minerals market. Steve Taylor is the Canadian mining market segment manager. He has over 30 years of experience in seal design, performance, troubleshooting, and installation for the mining industry. Mike Kaladimos is a global product manager with over 35 years of experience with seal application, manufacture, and design in the mining industry. And Tyler Smith is a global product manager for John Crane Diamond. He previously worked as an applications engineer at John Crane, specializing in engineering seals for severe duty applications. Welcome, guys. Thanks so much for joining us.
Thank you.
Thank you.
Before we get started with the Q&A, we do have a polling question. So can we just bring that up? Let's see. Laura? Great. The question is, which of the drivers for change do you believe will best support your maintenance / operational strategy? And you can choose as many of these as you like. Environmental regulation, energy reduction, reduced or eliminated water consumption, increased mean time between failures, reduction in maintenance costs, or increased output as a result of increased mean time between failures. Give it a couple more seconds for these results to come in. Great. So Warren, Mike, Steve, Tyler, are you seeing any surprises here with these poll responses?
No, not at all. I think if you lean back to the section that I covered, it's Warren speaking, by the way. One of the key drivers was environmental issues as well as in-country regulation. So the results don't surprise me at all. Mike?
Yeah, they really come down to, you're absolutely right, Warren. They come down to environmental regulation, and you could almost throw a rope around that, and water consumption reduction, because those two will drive a lot of decisions, I believe, in the future. And it's great to have technologies that address those like directly. So I agree with you.
These answers have changed a lot over 30 years. 30 years ago, reduction of maintenance costs and mean time between failure, top of list. Environmental regulation, what the heck is that? So yeah, nice to see the shift out there, voters.
Definitely.
So we do have some questions from the audience coming in, but I'd like to invite any more questions. You can submit those through the chat function if anyone has them. But our first question is for Tyler, and it's about diamond seal technology, which was just at the end of that presentation. You mentioned intermittent dry running during the presentation. Can you elaborate on how long the diamond seal can run in these conditions?
Yeah, so it's a great question, and it can be a challenging question to address. It's really dependent on the specific application. But what I can share today is we do run testing to illustrate the point that diamond can run longer than other conventional seal face materials. And what we're doing in that test, we're just running a comparative test on a ANSI Gould's 3196 pump with a type 5610 John Crane seal in it. And we'll run the pump at steady state conditions for about an hour, make sure everything's running properly. Then we'll completely drain the pump of any fluid, close off the suction valve. And then what we're doing is we're dynamically measuring the temperature at the outside diameter of the primary ring, which is a stationary ring in this arrangement. And we're seeing how long does it take for the temperature to rise up to 500 degrees Fahrenheit, or 260 degrees Celsius. And why did we choose that temperature? It's really due to that being a common elastomer material temperature limit. And basically, to summarize the data that we see, on average, when you run silicon versus silicon, it takes less than a minute for that to reach 500 degrees Fahrenheit. 260 degrees Celsius. Carbon versus silicon takes about 6 minutes on average. And then silicon versus diamond can run about 17 minutes to reach up to 500 degrees Fahrenheit. Diamond versus diamond can run about 34 minutes. And then actually our best material combination is graphite loaded silicon carbide versus diamond. And that's due to the lubricating properties of the graphite loaded silicon carbide running against the diamond material.
Another question for Tyler. Is it feasible and cost effective to have diamond faces versus diamond? And what would the coefficient of friction be in this case?
Yeah, certainly feasible to do that. The coefficient of friction in that case would be similar to what we see with the silicon versus diamond, so 0.018. Where in comparison to carbon is around 0.1. So again, it's about 18% of the frictional value of carbon versus silicon. And the reason why I say it is feasible and cost effective is because one, a lot of our customers are seeing an increase in MTBR, which is the main driver for payback period, but we're also seeing payback periods that can be calculated due to the power consumption savings on the motor with less losses due to frictional waste.
And Tyler, not to put you on the spot, but just one more question for you here. I have heard about diamond seal faces from other seal manufacturers outside of John Crane. What makes John Crane's diamond seal faces different?
Yeah, so I'll try to be short so I don't cut off Steve, Warren, and Mike with their expertise. But really, the three main differences between our product and what some of our competitors are offering, it really comes down to three things for me. And the first one is how the material is actually produced and what the resulting material looks like. And so when I talk about the grain structure of the ultra nanocrystalline diamond, that means it has a very fine grain structure, which enables our product to run against other hard faces. So for certain applications, you may be able to use the silicon versus diamond. So to that point, we have more value for our customers there. The second main thing is due to it's an intellectual process that we follow to get the adhesion of the diamond film to the silicon carbide to actually be stronger than the silicon carbide itself. So what I mean by that is actually if you were to pull off the diamond from the silicon carbide would come off with it. The adhesion is actually stronger than the silicon carbide itself, and we certainly do not see that from other vendors that are supplying diamond mechanical seal faces. And then the last thing I'd like to say is, to our knowledge and to public knowledge, we're the only seal vendor that has this technology in-house. And so what that means is when we're providing you with diamond mechanical seal faces, John Crane Diamond's sole purpose is to support John Crane and our customers. We don't have other interests in other industries outside of rotating equipment. And so to that point, we offer the best support and availability with our products.
Great, thank you, Tyler. The next question is for Mike, and this is about tailings transmission equipment. When you visit mine operations, what observations stand out about tailings transmission equipment, Mike?
I think, yeah, that's a pretty good question, and one that is really striking from mine to mine, from operation to operation. The symmetry and kind of the similarity between these tailings trains is I think, mechanically nearly identical, but technology-wise, there's a real diversion between how these pumps are being sealed. Some with two-bulk glands and packing, which is a ton of water required, and we saw the polling questions, and then others with mechanical seals and ultimately with dynamic lift upstream pumping seals that use a tiny amount of water when compared to packing, probably 1/100th of the water required for packing. So it's striking how similar they are in arrangement and how divergent they are in terms of technology choices that have been made by the mine. So it's a good question.
A second question for you, Mike. Why would an operation choose dynamic lift seals if, as you say, one can point to generations of shaft sealing technology in any given tailings train?
That too is a question that we get a lot of. Why do I need this? And I think the animation, I fall back on the animation because it's such a great tool to look at how much water is actually required to provide really a perfect lubrication regime for two opposing seal faces. Something that you're not going to see in any other arrangement of a seal or in certainly not in mechanical shaft packing, that a perfectly clean, minimized but super stiff lubrication pad of water, pure water, is what's levitating the faces and kind of providing perfect lubrication. So water consumption, 1/100th of an opposing example, and certainly MTBR, life of the product is vastly improved over something like packing or even a well-designed mechanical shaft seal. So yeah, it's a good question, and it's a huge topic. I mean, I could take longer than Tyler took, but I won't do that.
Thank you, Mike.
Sure.
So the next question is for Steve. Let's get you in here.
Sure.
As someone who spends more time thinking about mechanical seal faces than the inside of a concentrator, what new things have you learned from being on site for seal installations?
Well, plenty. I've been on site a bunch of times now, but I'm telling you, the first time arriving at a remote mine, it's an eye opener, and the stuff we see in a nice clean piece of paper at John Crane is quite a variance between what the real world's all about. One of the big things I've noticed and realized we need to be aware of when we show up on site is where in the heck is this water coming from? Because there's a pile of sources on site that Joe engineer back at the table doesn't realize he has at his fingertips or has to decide on. So like, is it going to be processed water, reclaimed water, raw water, potable water, or no water at all? That was interesting. And again, like I talked about in my part here, be aware of the hardened parts. It's a bit of a surprise when you deal with the pump on site when the shaft is so hard and the set screws that look so great back at your John Crane CAD program table that, gee, those set screws don't seem to want to grab onto this stuff so much. So yeah, be aware. The other big thing is I found shocking my first trip to a mine dealing with these slurry pumps, where the flexibility of these slurry pumps compared to other industries, that it's a lot easier to swap out and interchange parts than, say, if you're used to working with a pump in a refinery or a water treatment plant or somewhere. They wear out so fast sometimes that over the years, the slurry pump companies have made them more conducive to working on than some other pumps where you don't see them maybe 5 years down the road. So that's a good thing. It's easier for us seal characters to deal with and to fit our stuff into. So just a couple notes.
Another question for Steve. What tips do you have beyond seal and pump design selections?
What tips? Well, let's get away from the technical stuff here. Then the diamond faces and the upstream pumper. Let's talk about the soft problems. I'd say maybe these would be notes to selves as a seal vendor, whether you work for John Crane or anywhere else. But the sites should be aware of make sure that whoever's going to site to lend a hand is actually there to lend a hand and not be somebody that stands around and gets in the way. Know what you're doing. Everyone on site is busy and they're not there to hold your hand. Recognize that you're going to a remote site seal person or vendor, and don't just, you can't run to your local machine shop if something doesn't fit. Do your homework. If you're bringing somebody on site, don't bring on Joe Slick salesperson. If you have introvert, really smart technical guy on the other hand, pick Joe introvert who knows what he's doing. You don't need a slick sales guy showing up to lend the people a hand. So yeah, just make sure you get your people skills straightened out as well. I think at John Crane, we have a lot of really super experienced guys that you can tap into. So I guess to pat us on the back, you are dealing with a competent outfit, so we can get you the right guy on site.
Great, thanks. A question here for Warren. What is the most cost-effective way of reducing the total cost of ownership on gland packed pumps without converting to mechanical seals?
Oh, that's a question we get asked quite frequently, and it's relatively easy. Ultimately, you need to redesign the stuffing box because the stuffing boxes have never changed over the last 15 to 20 years. Packing has evolved. We understand that there are different technologies available, but to get those technologies to work as they should, you need to redesign the environment they work in. And for us to achieve the ultimate goal of reduced total cost of ownership, we need to adapt the stuffing box and make it conducive for the packing to work at its maximum. To do that, we got an option. We can put in a bushing into the stuffing box to reduce the length of the stuffing box so that we're sealing at its optimal area. And to do that, we'd use a product called our CPR bushing. And basically, this incorporates a bush made out of a modified ePTFE, say 25% graphite-filled PDFE, incorporating a lip design on the back of the bushing unit. And what that does, it takes the back two packing rings out, brings in the lantern ring, combines it into a single unit, protecting the packing from solids. Should the gland surface water drop, the little positive lip at the back closes onto the shaft, stopping the solids from getting under the packing and causing sliming of the pump, where everybody knows once it slimes, you need to repack. So ultimately, you can now change the front end to a really high quality packing and change to the carbon and graphite technologies. Once you're using the carbon and graphite technologies, you're going to get reduced power consumption, you're going to get reduced water consumption, and increased reliability there and then. You don't have to use an overly hardened sleeve with it. You can use a standard pump sleeve on it. The lip is only going to come into contact with the shaft should the gland surface water pressure drop below the stuffing box pressure. Then the lip comes into contact with the shaft. As the gland surface water restores, the lift lifts up again, and we effectively seal the pump. So that is the easiest, most cost-effective way to gain extended life out of packing. Implement a CPR bushing system. Thank you.
Great, thank you. A question for Steve. How does pump operation affect seal performance?
Hugely. There's so many ways pump performance. Well, if your pump is run dry, then you better make sure which will often happen in a mining application or in a super thick slurry, you better make darn sure you have your support system in place, whether it's a set of diamond faces that can handle a rough go or an upstream pumping that provides its own liquid film up from the outside, or even a dual seal. And something very interesting Mike and I actually ran into on site when we were working on a tailings train is we have to recognize how these pumps are being started up, especially VFDs. And some seals, it's not a deal breaker, but we need to know up front what's going on as far as the speed of the pump. Do you start the pump up, just hit the button, it's 1800 RPM, or do you slowly ramp it up to 500 RPM for half an hour and then go full speed? That's sort of important in some of our seal designs. Again, we can design for it, but don't hit us with that secret when we first show up on site and don't see it coming at us either. So have the talk.
Yeah.
Lots of cooperation and communication needed, I guess, right?
Mm-hmm. Yep.
I think you just got one more question here. And I think anyone who wants to answer it can answer it. Is John Crane looking at adding diamond to split seals?
Yeah, I can take that one on. There are a few. I'll be short with it. There's a few challenges that we're looking at to be able to offer that technology on split seals. It is something we're looking at, but we don't have a timeline as far as when that solution will be offered.
Okay. So I think that we're out of time now, but thank you so much, everyone, all of our experts and all of our audience for joining us today. Any questions that they weren't able to answer today, they will answer by email. So you will get a follow-up email from John Crane. And if you have additional questions for any of these experts, you can email them directly or email Elsa Cantu, the marketing manager, directly at elsa.cantu@johncrane.com. And I think that's it. Thank you so much for joining us.
Thanks, everyone. See you later.
Everyone.
Thanks very much.
Stay safe.
Take care.